Hey folks, welcome to your first Chemistry 2 video notes of the new calendar year. In today's lesson, we're going to discuss stoichiometry and the mole, found in Chapter 9 of your textbook. You'll learn what stoichiometry is, what the mole is and how to use it, how to use stoichiometry based on reactions, how to deal with limiting reactants, what combustion analysis does for us, and how to turn your molecular formula into percent compositions. Let's get started. As you know, a balanced chemical equation is basically just like a recipe in cooking. It tells us what ingredients or reactants we need in what quantities in order to make a certain amount of food or products. Let's stick with our example of hydrogen and iodine coming together to form a hydrogen iodide. If you'll remember, this balanced equation tells us that if we react one molecule of H2 with one molecule of I2, we'll get 2 molecules of HI. Using stoichiometry, we could determine how much of our reactants we need to make, say, 10 grams of HI. Stoichiometry is the study of quantitative or number-based aspects of chemistry. It's how we find the answers to questions like, how much of this will I produce? Or how much of this reactant do I need? Stoichiometry is nothing more than unit conversions and dimensional analysis, which we already studied quite a bit in Chapter 2. Let's take this recipe for making a cheesecake, for example. Our recipe says that it takes 3 blocks of cheese, 5 eggs, and 1 cup of sugar to make 1 cheesecake. What if I wanted to know how many eggs it'll take to make 2 cakes? That's some simple math that you probably just did in your head, but to help introduce you to the idea of stoichiometry, let's write it out using dimensional analysis. You start with the quantity you're given, 2 cakes. We want to convert that from cakes to eggs, so we need a conversion factor for that. According to our recipe, for every 1 cake, it takes 5 eggs. We want to put the cake on bottom so the units cancel out, so we'll multiply our 2 cakes by 5 eggs over 1 cake. This tells us that it'll take us 10 eggs to make 2 cakes. The nice thing about this method is that we can use it to convert any reactant to any product. Say I only had 3 cups of sugar. How many cakes would I make with that? Start your problem the same way, but this time use a conversion factor that takes you from sugar to cake. In chemical equations, or this recipe even, the numbers in front of each reactant or product, the coefficients, tell us how many atoms or molecules of each substance are involved in this process. It's important to remember that those numbers don't speak in terms of mass of those substances, only the number of particles. Perhaps we were told that we had 24 ounces of cream cheese. That doesn't really help us figure out how many cheesecakes we could make. But if we know that each block of cream cheese has a mass of 8 ounces, then we can convert the mass to the number of blocks and then convert that number to the number of cheesecakes. Our substances in a chemical equation work the same way. But to convert from mass to molecules, we need something called the mole. We can never, ever convert directly from grams of one substance to grams of another using a balanced chemical equation, because balanced equations only talk about the number of atoms or molecules. For instance, if I wanted to make 10 grams of hydrogen iodide, I couldn't just assume that that would mean I need 5 grams of hydrogen and 5 grams of iodine to react. Even though they react in a 1-to-1 ratio, that 1-to-1 ratio means there's 1 molecule of H2 for every 1 molecule of I2. H2 and I2 have drastically different masses, so we can't compare them using grams. This is where the mole comes in handy. You know that 1 dozen of something is equal to 12 of something, right? The mole is the same concept. 1 mole of something is equal to 6.022 times 10 to the 23 of something. This is known as Avogadro's number, and it can be used as a conversion factor to get from moles to particles or vice versa. Knowing this, we could read our equation as 1 molecule of H2 and 1 molecule of I2 react to give 2 molecules of HI, or we could say that 1 mole of H2 molecules and 1 mole of I2 molecules react to give 2 moles of HI molecules. Those both say essentially the same thing, but if we know the number of moles of a substance, we can get to the amount of grams using that substance's molar mass. The molar mass is how many grams 1 mole of a substance weighs, and the units are grams per mole. To find the molar mass, you add up the average atomic masses from the periodic table of each atom of each element in your formula. If you'll remember, average atomic mass is in units of AMU, not grams per mole. But because 1 AMU is defined as 1/12 of the mass of 1 mole of carbon-12 atoms, we learn that AMU and grams per mole end up as the same quantity, just different units. So if I wanted to find the molar mass of, say, CO2, I'd add up the mass of 1 mole of carbon atoms, 1 mole of oxygen atoms, and another mole of oxygen atoms. Or, as a shortcut, I could add up the mass of 1 mole of carbon atoms and 2 times the mass of 1 mole of oxygen atoms. Either way, I end up with 44.009 grams per mole of carbon dioxide. Water has a molar mass of 18.015 grams per mole. You can see here how it can be used as a conversion factor in dimensional analysis. Since the molar mass is how many grams there are in 1 mole, the conversion factor will always have 1 mole on one side and however many grams the molar mass is on the other. At this point, you should be able to convert between moles and grams using molar mass, and between moles and the number of atoms or molecules using Avogadro's number. Here's a handy chart that helps summarize those two types of conversions. Now that we can convert between particles, moles, and grams, let's talk about how to use these conversions with reactions. We usually think of balanced chemical equations as being perfect and always producing expected results. But the problem is that most of the time some of our reactants participate in side reactions that we're unaware of, or we have difficulties isolating our products. So the amount of product we end up with isn't exactly what we would expect. That expected amount, or the maximum amount we could hope to possibly make given the amount of reactants we have, is called the theoretical yield. The actual amount of product that you end up with is called the actual yield, or experimental yield. Using those two values, we can calculate a ratio of the actual to theoretical yield, which we call the percent yield. The closer that percent yield is to 100%, the better we did on our experiment. Usually we'll have a theoretical yield less than 100%, but sometimes we end up with more than 100%. How can this be? How can we make more of a product that we didn't have enough reactants to make with? That's usually caused by some issue in the isolation process. If your product is still wet or contaminated with some other substance, when we measure its mass, we're measuring more than just the mass of the product. So it appears heavier than it actually is. Anyway, let's put this into practice. Our reaction says that 1 mole of H2 will react with 1 mole of I2 to produce 2 moles of HI. The molar mass of H2 is 2.0152. The molar mass of I2 is 253.810. And the molar mass of HI is 127.913. If we multiply all of those by their coefficients, 1, 1, and 2 respectively, we'll see that we react 2.0152 grams of H2 with 253.810 grams of I2, and we should produce 255.826 grams of HI. That's our theoretical yield. Say I perform this reaction and only produce 225.10 grams of HI. To find the percent yield, I take my actual, the 225.10, divided by the theoretical, or 255.826, and then I multiply by 100. This gives us about 88%, which is a pretty good percent yield. If we put the knowledge of conversion factors that we learned in 9.2 to use, we can convert between any one of our reactants or products. I still want to know how many grams of H2 I need to react in order to produce 10 grams of HI. We can mathematically reason that out now. Here's all of the possible conversion factors we could possibly need to get between moles and molecules. From our balanced chemical equation, we see that for every 1 mole of H2, there are 2 moles of HI. For every 1 mole of I2, there are 2 moles of HI. And for every 1 mole of H2, there's 1 mole of I2. From our molecular formulas, we can also see that there are 2 moles of hydrogen atoms in every 1 mole of H2 molecules, and we can do the same for I2 and HI as well. The first step to figuring out these kinds of questions is to write out your balanced chemical equation. From our question, we know the value of HI we're shooting for is 10 grams, so let's write that underneath HI. We don't know H2 or I2, so we'll put a question mark under them. We're looking for how many grams of H2, but we can't convert from grams of HI to grams of H2 directly. We can compare moles of HI to moles of H2. So let's convert our known 10 grams of HI to moles using its molar mass. Now that we have moles of HI, we can convert to moles of H2 using the coefficients from the balanced equation. And now that we have moles of H2, we can convert to grams of H2 using its molar mass. The two most important things to remember when doing these problems is to write out your whole units, such as grams of HI or moles of HI, and to make sure that your units cancel. Writing out the whole unit will help you keep track of things and not get lost. The more information you write down, the easier it is to see how your units can cancel. So far, we've been assuming that we have the exact correct amount of reactants. But what if we have more or less? Just like when we had only a limited amount of sugar but plenty of other ingredients, the sugar limited the amount of cheesecakes we could make. That's what we call a limiting reactant. It's a reactant that's in short supply relative to the other reactants in the equation, and it limits the amount of product that we can make. Any reactants that have more than enough compared to the limiting reactant are considered excessive reactants, and they won't get all used up in the reaction. We'll have leftovers. If we don't have any limiting reactants because we managed to use the exact correct amounts of reactants, the reaction is said to be performed in a stoichiometric or balanced fashion. When there is a limiting reactant, we say it was performed in a limiting fashion. Since the limiting reactant limits the amount of products we can make, we have to use the limiting reactant to calculate the theoretical yield. So how do we know which reactant is limited? Well, you can follow these steps to determine that. Write out your balanced equation, convert the grams of each of your reactants to moles, and then divide each of those mole values by the coefficient in the equation to get a mole to coefficient ratio. Whichever reactant has the smallest mole to coefficient ratio is the limiting reactant. If you want to find the theoretical yield, you just convert the moles of your limiting reactant to moles of products, and then convert that to grams, molecules, or whatever the problem is asking you for. So, for example, in the combustion of propane, 1 mole of propane molecules reacts with 5 moles of oxygen molecules. If I'm told that I have 264 grams of propane and 928 grams of oxygen, I divide each of those by their molar masses, and I determine that I've got 6 moles of propane molecules and 29 moles of oxygen molecules. That's not enough to determine our limiting reactant yet because these two substances don't react in a 1-to-1 ratio. So we divide by their coefficients, 1 and 5, giving us 6 and 5.8 respectively. This means that after 5.8 rounds of molar reaction, we'll run out of oxygen molecules and have leftover propane molecules. Therefore, oxygen is our limiting reactant. From there, I could convert my 29 moles of oxygen to moles of carbon dioxide or water, and then to grams or molecules of that product if I were asked to. Combustion analysis is a handy-dandy method of determining the percent composition of a compound. If we burn a sample of a substance in the presence of excess oxygen, and then collect all of the CO2 and H2O that's produced, we can determine the percent composition, which helps us to determine the empirical formula. First, make sure all of your percents add up to 100%. Then, assume that you have 100 grams of your substance. This allows you to change your percent mass to grams. Convert the grams of each element into moles using their molar masses. This gives you the subscripts of your formula. We don't really like decimal numbers in our subscripts though, so to get rid of those, we divide by the smallest of them. This usually gives us something very close to a whole number. So we round to that whole number. If you perform this step and end up with something more than, say, 0.1 away from a whole number, you might have to multiply all of the subscripts by a factor that'll get rid of that decimal. For instance, if we did all of this work and got, say, 2.25 for one of our subscripts, we'd want to multiply all of our subscripts by 4 to get rid of that 0.25. So, let's say we were told the percent composition of a compound suspected to be glucose is 29.94% carbon, 6.72% hydrogen, and 53.3% oxygen. Those add up to 100%, so we're good to go. Assume that each of those percents are just grams, and then use the molar mass of each element to convert from grams to moles. This gets us 3.33, 6.67, and 3.33, which we could use as subscripts. However, since we like our subscripts to be whole numbers, we'll divide by the least of those, which is 3.33. And that gives us 1, 2, and 1, respectively. So our empirical formula is CH2O. The molecular formula for glucose is C6H12O6, though. Does that mean this compound isn't glucose? Well, not necessarily. To find the molecular formula, you need the actual molar mass of the compound, which we could determine through a variety of different methods. As a quick reminder, the empirical formula just tells you the simplest whole number ratio of moles of atoms of each element present in a compound. The molecular formula tells you the actual number of moles of atoms present in 1 mole of that compound. So if we found the molar mass of our empirical formula, the CH2O, that is 30.026. Through another experiment, we found that the molar mass of our sample was 180.155 grams. To convert from empirical to molecular, you take the molar mass of your compound divided by the molar mass of your empirical formula. In this case, we get about 6. This means that each of the subscripts in our molecular formula are actually 6 times what they are in the empirical formula. So based on that information, it turns out our actual molecular formula is C6H12O6, so our compound is probably glucose. Lastly, let's work backwards and convert the molecular formula into percent composition. The first step is to assume that you have 1 mole of your substance. With that knowledge, we know that each subscript represents how many moles of atoms of that element there are. Therefore, for glucose, we have 6 moles of carbon atoms, 12 moles of hydrogen atoms, and 6 moles of oxygen atoms. Convert each of those to grams using the molar mass of each element. We can then add up all of those masses to get our total mass, or just use the molar mass of glucose as our total. We divide the mass of each element by the total, and then multiply by 100 to get the percent by mass of each element. Add up all your percents and make sure they equal 100%, or very close to, and then you're good to go. In this case, we calculated the theoretical percent composition was 40, 6.71, and 53.28% for C, H, and O respectively. This is slightly different, but very close to the 29.94, 6.72, and 53.34% we were told were found through combustion analysis. Well, that's all for today, folks. As always, let me know if you have any questions.